Hey chemistry class, in this video we're going to begin to look at section 2b. First, before we dive into that, let's look at where we are in the chapter. We are here on day 4 beginning section 2b, which we'll look at today and tomorrow. Today you should be finishing up the element note cards that I assigned you on Friday. If you need some extra note cards and you're at school, I have some in the room. And then tomorrow's homework will be to complete the digital section review over the material that we're going to be covering. On Wednesday, you're going to have a quiz over section 2b, and then we'll finish up the notes for the chapter by looking at section 2c. And all of this is heading for a test on Friday over chapter 2, all the notes. So even though I'm not going to be with you in class this week, we are going to keep to this schedule. And these homework assignments will be posted on Google Classroom. So as far as where we're at in your notes, we're not going to be doing the lab that's on pages 8, 9, and 10. Sorry about that. It might come up. There might be another place in the year that we can put it. But we're going to be picking up on page 12, which looks like this, and we're going to plan to fill in this whole page today, and then we'll do page 13 tomorrow. So that's where we're at in your notes. Let's go ahead and start looking at energy and matter. So at the beginning of the chapter, we started talking about matter, which is the physical stuff that makes up the universe, anything that occupies space and has mass. But it's not the only thing in the universe. The universe is made of two basic components, matter, the material physical stuff, and energy, which is the immaterial stuff that makes up the rest of the universe. Now, it's hard to define energy, just kind of like it was hard to define matter. So one kind of working description that we have for energy is that energy is the ability to do work. It's what moves matter or lets matter do some work. Work, by the way, is a force moving matter through a distance. So you're able to, that's where it connects to the matter part of the universe. It's allowing matter to move. All right, so we have this energy, this ability to do work. Energy comes in different forms. So let's just mention some of the different forms of energy, though there's certainly more than this. There's mechanical energy. Mechanical energy would be motion, basically, but there's also two subcategories of mechanical energy that you'll want to write down. It could be kinetic energy, K-I-N-E-T-I-C, which is actual motion. Kinetic energy is the energy of motion. Or you could have potential mechanical energy, and that's energy due to your position. So if you take an object and you raise it up in the air, you're giving it some energy, potential energy based on its position. It has the potential to move. So mechanical energy overall has to do with motion. Kinetic is actually in motion. Potential mechanical energy has got the potential to move because of its position. All right, thermal energy would be energy involved in heat. We're going to come back and talk a little bit more about thermal energy in a moment because it's got a more nuanced definition. There's acoustic energy, which is to do with sound. Electromagnetic energy would be involved in electricity. It would be the energy that's involved in, the attraction of magnets and things like that. But it's also the energy that's behind light. Light is electromagnetic waves that are moving. It's also the energy involved in X-rays and microwaves, and anything in the electromagnetic spectrum would be electromagnetic. Chemical energy is going to come up a lot this year. It's the energy involved in the bonds that hold atoms together. And then we've got nuclear energy, which we'll look at the very end of the year. It's the energy involved in holding the nucleus together. And when you make changes in the nucleus, it actually releases a lot of nuclear energy. That's the energy behind nuclear power plants. Okay, so we're just going to go ahead and dive in and talk about thermodynamics. There's a definition for thermodynamics, and then there's a couple laws of thermodynamics that we're going to talk about as well. So first of all, for the definition, it studies the flow of energy, and it's primarily concerned with thermal energy or heat energy. thermodynamics studies the flow of energy, particularly thermal energy. Like I said, there's two laws of thermodynamics. That's what the end of that sentence says, two laws. And they both have two names. So there's the first law of thermodynamics, which has a second name, and then the second law of thermodynamics, which has a different name. And I've got the other names listed on your notes there. The first law of thermodynamics states that matter and energy can neither be created nor destroyed, only converted from one form to another. So this is going to come up in the chemical reactions that we observe. You're going to put two substances together, there's a reaction, and they change into new substances, but none of the matter has gone away. Even if it looks like it's gone away, like the paper that we burned as an example last week, it looked like the paper's completely gone. But actually the molecules were torn apart, and then the atoms reformed into new gas molecules that were floating around in the air. We didn't actually destroy the molecules or the atoms that made up the paper. Now, some of the matter was actually converted into a little bit of energy that we saw in that heat and light. So you can convert one type of matter to a different type of matter, one type of energy to a different type of energy, and sometimes matter to energy or energy to matter, but you're never either creating or destroying either of those things. The other name for the first law of thermodynamics is the law of conservation of mass energy. When you see the word conservation in a science class, it has to do with the idea that things are staying the same, not being lost or made new, like it's saying in the law here. So that means that outside of supernatural events, the total mass of the universe has remained constant since creation. God created that matter at the moment of creation, and then it's just stayed the same since then. Now you can convert between different forms, like we mentioned before. So you can take the nuclear energy, that's the energy that's powering the sun. It gets converted into electromagnetic energy. It travels to us as infrared and light waves. That heats up the atmosphere, and now we have thermal energy, which makes the atmosphere move around as wind, and that's a mechanical energy. We can capture that as electricity, and then use that to store in the form of chemical energy. So again, it is possible to convert from one form to the other. You just never destroy the energy. Before we move on to the next law, let me just show you a Bible verse that kind of alludes to this idea. But the heavens and the earth, which are now, by the same word are kept in store, reserved unto fire against the day of judgment and perdition. So the reserved, everything's conserved and staying the same now that it's been created. All right, now, even though we are able to convert the energy between the different forms, we do end up losing some of the energy. And by losing, I don't mean that it's destroyed or not there anymore. It's just not in a form that is usable because it's gone out into the universe, like heat energy that radiates out of the atmosphere. It's not in a place or state that it's usable to us. There's an idea behind this facet of energy called entropy. Entropy is a measure of the dispersal of energy. You might have heard it sometimes in the past as disorder, the randomness or disorder in a system, which is sort of true, but this is a better description of entropy. The idea that energy goes out and disperses. It doesn't want to stay close together, and it, because of that, can end up in a state or location where it's not really usable anymore. That leads us to the second law of thermodynamics, which is sometimes called the law of entropy. It says that natural processes tend toward the highest entropy or the minimum usable energy, because again, when it spreads out, it's not really in a state that we can use it. So any natural process tends to disperse energy. Because it's got entropy as part of its definition, we sometimes call this the law of entropy, and that's the synonym that you need to know for it. Now we can see that in, again, natural processes like decay or growth and things like that, things tend toward a state of disorder. That's where you can kind of see the disorder definition come back, if they're just left to their own devices. Again, the decay or something of any living thing would be an example of entropy. That energy that was there is dispersing out, and we're losing the ability to capture it. There's a verse that kind of alludes to this as well in Hebrews. And thou, Lord, in the beginning hast laid the foundation of the earth, and the heavens are the work of thine hands. They shall perish, but thou remainest. They shall all wax old as doth a garment. So again, even though they're not being destroyed yet, waxing old, aging, not being usable anymore, that's kind of the idea that we were talking about with the second law of thermodynamics. There's one other term that's in your term list, it's on Quizlet, that we can talk about with these laws of thermodynamics. It's called the system. The definition that you need to know for system is it's the portion of the universe that is under study. The portion of the universe that's under study. So that could be the little chemicals that you have inside of a beaker, and it could include the beaker as well. You know, you're studying those chemicals and their reactions, that's your system. Everything outside of that system, we're going to call surroundings, and we imagine the system as separated from the surroundings by a boundary. So the system is the portion of the universe under study, and it has definite boundaries. Now, it might not be a physical boundary that you can see or feel, but we imagine it to have boundaries. With the chemicals in the beaker, the edges of the beaker could be considered your boundary, but even the imaginary top of the beaker that's not covered would be a boundary as well. So the system always has definite boundaries. Everything outside the system is called the surroundings. All right, let's move on, and we're going to look at the difference between thermal energy, temperature, and heat. Three terms that seem to all have the same idea in our heads maybe, but they do have slight differences in their definitions, and we're going to make sure that we can get those definitions. Now, in order to understand the differences in the definitions between thermal energy, temperature, and heat, we need to understand this foundational principle of chemistry. It's not something that people have agreed on at all times in the past, but we pretty much do now. It's the idea that all matter is made of tiny particles, think atoms, molecules, that are in constant random motion. Now, all matter being made of tiny particles, that's something that you probably just accept, like, of course it is. Atoms and molecules, you've heard of those all your life, but you've never seen them. Like, we don't have any actual visual proof that they're there. We have some microscopes that are getting good enough now that we do have more proof. But we had to kind of prove this through some experiments and try to observe what can we see with our eyes that can only be explained if matter is made of tiny particles in constant random motion. So there's two phenomena that you can, observe with your eyes that are proof of this statement. So these next two terms you should associate as being proof of the fact that matter consists of tiny particles. We've talked about both of these ideas in previous classes. One is diffusion. Diffusion is the spreading out of matter. The spreading out of matter. It'll go from an area of high concentration to low concentration. So at the beginning of this video clip, there's a high concentration of that brown bromine vapor at the bottom of this cylinder, and it's naturally spreading out over time. Now, the reason that it's spreading out, the way that we can explain why that vapor would be spreading out relates back to, well, what if the vapor is made of tiny, tiny particles and the air above it is tiny, tiny particles and they're in constant motion? What would that look like? Well, it would look something like this. The bromine, the air, they're both in constant random motion, and because of that motion, they're going to collide with each other. They're going to collide with particles that are like them, particles that are not like them, and bump and change direction, and just naturally go past each other and end up spreading themselves out. Where if those particles were just stationary, they wouldn't necessarily spread out because they don't have the motion to go from one place to another. So that's diffusion. The second phenomenon that's proof that we offer as proof that matter consists of tiny particles is called Brownian motion. The quick description for Brownian motion, it is the random jiggling of microscopic particles. Random jiggling of microscopic particles. So the idea here is, imagine you're looking under a microscope and the white spheres would be like pieces of dust or something that you could see that you've got in some water. And those pieces of dust will look like they're moving around, and the explanation for why they're moving is that there's little water molecules that you can't see that are in constant random motion, and they're colliding with the larger particles that we can see, causing them to move in this random jiggling way. So the Brownian motion is the term for that random jiggling of the dust that you can see, but it does that because of the motion of the water particles that we can't see. The water is made of tiny particles that's in constant random motion, colliding with other particles. Okay, so now that we have this picture in our head of matter being made of tiny, tiny atoms and molecules that we can't see, but they are in constant motion, now we're ready for the definitions of different kinds of energy, heat, temperature, that sort of thing. Okay, so I'm going to set it up this way. We've got energy, temperature, and heat, and actually have a couple types of energy that we're going to look at. These are not synonyms in chemistry class. There is a difference between them. So let's look at a couple different types of energy and then how the definitions relate to each other. You can set up a little chart like this if you want. I'm going to focus on how the terms relate to each other rather than writing out full definitions, but if you want to write down the full definitions, you can make a space for that as you have room. Okay, so the first kind of energy that I want to look at is kinetic energy. We mentioned that a little while ago. Kinetic energy is the energy of motion of the particles. So those tiny particles in constant random motion, they have kinetic energy because they're moving around. So kinetic energy is the actual motion of the particles. Thermal energy has to do with an entire sample. Thermal energy is the sum, S-U-M, sum total of the kinetic energy of an object's particles. So if you have, a sample of matter, I've got some coffee in here. The thermal energy of this coffee is the sum of all the kinetic energy of all the molecules of coffee that's in this container. So thermal energy is the sum of the kinetic energy. That's how those two terms relate to each other. So again, sum is adding all them together. That means if you have a large sample, it's going to have more thermal energy than a small sample because it has so many more molecules you can add up to make your total. So the size of the sample has a good bit to do with how much thermal energy it has. Okay. Then we have temperature. The basic definition for temperature is it measures the average kinetic energy of all of the particles in a sample. That's different than the total. You're going to look at all the kinetic energies of the particles in a sample, but then you divide it by how many particles you had. So you can say that a sample has a temperature of 30 degrees Celsius, and that could be a really large sample or a really small sample that both have the same temperature. Where their thermal energies, their sums would be different. The large sample would have a much larger thermal energy, even though it had the same temperature. All right, so now we have thermal energy, the sum of the total kinetic energy, all the motions of the particles. Temperature, the average kinetic energy. And then our last term here is heat. Well, let me come back and talk about heat in a second. Let's do a sample problem. You can see this at the bottom of the page. Which has more thermal energy, an ocean full of 60-degree Fahrenheit water or a test tube full of boiling water? All right, so I know that boiling is about 212 degrees Fahrenheit, so that's a much higher temperature. The average motion of these particles is much higher. That means the particles are moving very, very fast on average compared to the ocean's molecules. They're moving a little bit slower. But which has more thermal energy? Thermal energy is the sum of the motion of all the particles. So the ocean is going to have billions of quadrillions, like so many molecules, the number would be mind-boggling. Molecules at this slower speed, but you add them all together, you're going to come up with a huge sum of kinetic energy. Where the test tube only has billions of billions, not quadrillions, and it's a big number, but it's not nearly the number of the ocean. So even though each of those molecules would have a higher kinetic energy that they're adding into the total, they can't nearly reach the number that the ocean would have because of the size difference. So the answer here is going to be the ocean. On the test question, you're going to want to look for the choice that has the probably the largest amount, but it'll give you some different temperatures to take into consideration. So whatever is the largest amount with the higher temperature of the larger amounts, that's the one that you're going to go for. All right, let's go back and talk about heat. Heat is also related to these other terms. The definition for heat would be change in thermal energy. There's a few different ways that you could describe heat that might be helpful to write down. Besides change in thermal energy, it's thermal energy that's transferred from one object to another, thermal energy in transit, that sort of thing. You also need to know and write down the direction that heat is transferred. So heat is always transferred from a warmer object to a cooler object. Heat is always transferred from a warmer object to a cooler object, which makes natural common sense. I mean, if you hold a cup of coffee and that cup of coffee is very hot, it's going to transfer heat out of the cup and into your hands. So it's going from the warmer object to the cooler object. If you were holding a cup of ice water, then your hand is the warmer object and the cup with the liquid inside is the cooler object. So heat, if you were holding ice water, would go from your hand to the ice water. So you always warm up the cooler object. You would never have a hot thing with a cold thing and the hot thing gets even hotter because it's leaching heat or thermal energy out of the cold object. That never happens. And it sounds dumb to even say that it might happen, but that's going to help us with a definition that's going to come up tomorrow. Okay, so there we have heat, change in thermal energy. The last thing I have for this page is a contrast of two terms, two types of processes that are going to come up a lot throughout the year based on what kind of thermal energy is involved, the direction that the thermal energy is going. So exothermic, these are changes that release energy, and they could use any synonym for release there. So they release energy, they produce energy, they liberate energy. Those are exothermic processes. The energy is coming out, it's making the heat's being transferred out of the system into the surroundings. And then endothermic processes would be processes that absorb heat. So they bring the heat in, they absorb heat from the surroundings and store it maybe in chemical bonds or something like that. They change it into a different form. So exothermic versus endothermic. All right, we're going to stop here with our notes for today. For the rest of the time, you can finish up your element note cards if you haven't already. And if you have finished them up, go ahead and start studying. You need to be very familiar with, you look at the symbol for an element and you know its name, or you look at the name of an element and you can come up with its symbol. If I were to give you a tip, start off by looking at the symbol for the element and seeing if you can come up with the name. Learn it that way first. That'll really help you for your test. All right, I'll see you in the next video lesson.